Hello everyone, in this video we're going to be talking about magnets, and this is really aimed at key stage 3. So we're going to talk about just the basic bar magnet, what magnetic fields are and magnetic domains. We'll talk about things like attraction and repulsion, and then we'll delve into electromagnets, so what they actually are, how they're formed, and the ways that you can change them to make them stronger. So let's start with just a basic magnet. So we're just going to draw a very rough sketch of this. And this is typical of what you'd see in a textbook or on the internet. This is what's called a bar magnet. Often, especially in books, you tend to see one end as red. Let's shade that in red. And one end in blue. And an N and an S next to them. Now what the N and an S essentially mean are north and south. We say that the magnet has a north end and a south end, and this is called a bar magnet. So in this bar magnet we have a north end and we have a south end. And you could use this magnet to simply pick up any magnetic materials. Now, when we think of magnetic materials, we think of three. So there are three magnetic materials. And those are iron, cobalt, and the third and final one is something called nickel. Now, often in exam questions, they kind of throw out a bit of an unusual one because they talk about steel. Now, steel is an alloy, and that means it's a mixture of metals, and it actually contains iron. So steel, so I'll put here plus steel. Steel, because it contains iron, is also magnetic. So sometimes it's written as a fourth material, but it's only because it contains the iron. So iron, cobalt and nickel are three magnetic materials. Now, if you were to take, let's just bring this up. If you were to put one bar magnet next to another, you notice that they would either kind of like push apart or attract to one another. You'd actually find that if you were to put a north end of a magnet next to the north end of another magnet, then they would almost push away from one another. They would, what we say, repel each other. They push each other away. Equally, if we had and again, these are just very quick sketches. If we had a south end next to a south end, so the two blue parts together, when you put them together, you notice that they also would kind of push apart from each other. They too would repel. And it's only when you have a north end of one magnet and the south of another do you see that they almost like push together and almost join. And that is when we say they attract. Now I'm going to explain why you get repulsion and attraction. It's all to do with magnetic fields. So again, let's just reduce this down and move this up a little bit. And we're going to draw our bar magnet again at the bottom. We'll put in a north end here and a south end here, and we'll use just the same colours. We'll have the south end as blue and the north end as red. Now, around the magnet is something called a magnetic field. It's this region around the magnet in which anything that enters will experience a force. That's how we define a magnetic field, the sort of region around the magnet in which an object will experience a force, and that force can be a pushing or a pulling force. Now, if it's a pushing force, then it would be repelled. If it's a pulling force, then it's attracted to. So if I took a magnetic material, like an iron nail, for example, and brought it near to the magnet, it could be attracted because it's magnetic to this magnet. So that would be its attracting force. And it's actually possible with iron filings. If you were in a lab and were to sprinkle some iron filings on over a piece of paper and put a magnet underneath the paper, you'd be able to see and visualize this magnetic field shape. There's actually what's called magnetic field lines over this magnet. And often in exams you have to be able to draw this. So we're going to draw one together. There's a magnetic field line that comes out of the north. When we draw the field lines, they only have one arrowhead on, and the direction is important. So it comes out of the north, and there's one coming into the south. Now, because they're coming out of the north, at the edges you have ones that come out, but because they're close to the edge, they sort of veer off to the side, and they too are coming out. And equally, we have the magnetic field lines coming into the south, but they're coming in from the side, like so, and the arrowheads are important. Then we get this unusual sort of shape in the middle, where you have magnetic field lines that go almost backwards. They work from north to south. So we'll just draw in two, and they go back. They work from north to south. And that's really important that you learn the field lines where they are. So we have them coming into the south, out the north, and then going from north back over to the south. And that's a little bit about magnetic field lines. So let's think about domains. So again, we'll shrink this and just move it over to here. Domains is a topic that doesn't often come up, but within a magnet, you have tiny groups of atoms called domains, and the domains are in a certain direction. So those atoms are directed in completely different ways. Even in a magnetic material, so just a random piece of iron again or cobalt, you have these domains all pointing in different directions. And those groups of atoms, they are the domains. So the domains are these big groups of atoms. Now, if you were to stroke with a cloth a piece of iron in the same direction repeatedly, if you just keep stroking this from left to right, for example, then what you'd find is that all those domains would line up. All those arrows face one way. And when you do that, then it turns the material magnetic. You need those atoms, those groups of atoms to align, face the same direction, and it will then become a magnet. The only way you can disrupt that and remove that sort of magnetic property is by heating the magnet or actually hammering it. Because if you were to just break it in two, what you'd find is even when you break it in two, you'd still keep a sort of north and a south end on the two bits. So the only way you can get those groups of atoms or those domains to realign in completely different directions is by heating it or actually hammering it. And that's how you can turn a magnetic material into a magnet, essentially by making sure all those domains are in the same direction. One other little experiment you could do in a lab relates to the fact that magnetism doesn't pass through magnetic materials. I just want to explain what I've what I essentially mean by that. Let's imagine we have a desk here, school desk, and we've got a piece of string, and at the end of that piece of string we've got a paper clip just here, and we're hovering above that a magnet. So normally the paper clip would just fall to the floor, but we're able to attract it to that magnet and keep it hovering up with this tiny gap here remaining, this gap between the magnet and the string. I'll just make it clear. I'll just actually just divide the page up just so we can see we're looking at this bottom quarter. Now, if I were to get a piece of paper, and put it here, then the paper clip will stay standing. It will still attract to the magnet. Magnetism will pass through that paper, so those field lines around the magnet will still be present. So where I'm putting the asterisk now, all these field lines on this diagram, all the arrows here, would still be around this magnet. I'll just draw them in very quickly. And you'd still be able to attract the paper clip. If, however, instead of paper we used a magnetic material, like a piece of cobalt, the magnetism can't pass through a magnetic material. You change that kind of nature of the magnetic field, so now the cobalt is attracted to the magnet, and we lose all attraction of the paper clip to the magnet, so now the paper clip will fall. It's just a little aside, but it's a little practical that you can do in a lab just with a paper clip, bit of string, magnet and a few different materials to put through that gap. So let's think about electromagnets next. Let's take our example of an iron nail. I'm just going to draw it just in here. So here's just a regular little iron nail. Now, an electromagnet, as you can guess from the name, is a magnet that's essentially brought about by the use of electricity. And unlike the bar magnet, you can actually turn the magnetism off. So you can use the electricity to turn the magnet on, but equally if you turn the electricity off, you lose the magnetism. And this is how you make it. If you wrap a coil around a magnetic material, like this piece of iron, so here's a coil and we're imagining we're wrapping this magnet around, and we'll take this back to a battery here. Not the best sketch, but still. So you've got a very simple circuit drawing, not drawn particularly well, but you get the idea. So you've got a battery, and this coil is wrapped around this iron nail. When electricity flows through the coil, it produces a magnetic field. So we get a magnetic field being produced around this nail. And when that happens, that nail becomes a magnet. So we magnetize that iron nail. If we were to turn the electricity off, it would lose that magnetism. So you turn the electricity on, current flows through the coil, and it creates this magnetic field around the iron nail in the middle. So if we brought a magnetic material to it, like, I know, a coin or a paper clip, it would attract to this iron nail. And there are 3 ways you can actually strengthen an electromagnet. So this here is an electromagnet. And there are 3 ways that you can increase the strength. So one is to use more coils. More coils around the iron would allow more electricity to flow, strong magnetic field. The second thing would actually to have more electricity thrown through the circuit. So actually more current, increase the flow of electricity in the circuit. And the third and final way to improve an electromagnet is to have a stronger iron core. Now, a stronger iron core essentially means like a stronger middle piece of iron, a bigger iron core, bigger sort of chunk of iron, if you like, that we're wrapping the coil around. That a bigger wadge of metal, if you like, will increase the strength of the electromagnet. Now, electromagnets have many, many uses. They're used in relays, which are smaller circuits essentially used to turn on larger ones. But quite often in school, they're used in this example. Now, what we have here is an electric bell. We're just going to explain, and we'll finish on this electric bell and how it works. So, if we just have a look, we've got a battery at the top, we've got a switch over to the side, some coils here, we've got an electromagnet in the middle with this black coil wrapped around it. Then we've got this spring, and attached to the spring is a hammer, and we've got a gong. And you can see that on this spring, we've got something called a soft iron armature. An armature is just kind of like a piece of iron that the spring's attached to. And here in red, we can see that we have a piece of that spring attaching just there to this contact, this piece of sort of blue material here on the diagram. So here's our basic setup. Now, if someone were to press the switch, then we'll complete the circuit, current would flow. So we'd have current flowing down here, through this wire, and it would flow through these coils in this electromagnet, and it would turn that piece of material into a magnet. So we'll get a magnetic, or a magnetic material essentially in the middle of this picture. Now, when we turn this middle part into a magnet, it will attract the iron, this piece of iron that we have here that I'm just colouring in blue. And attached to that iron is the hammer. So you can see that the moment this grey material in the middle becomes a magnet, it will attract the iron, and the iron armature will swing across to the left because it's attracted to the magnet. And when it swings across to the left, the hammer will too swing to the left and hit the gong. So you press the switch, the bell rings. But notice the moment that the hammer moves across to the left to hit the gong, you will essentially pull the spring away from that contact. And when that happens, you break the circuit. And when you break the circuit, no electricity can flow. So this iron moves to the magnet rather. The hammer then moves to the gong and hits it. But where I've drawn the X, that bit would break, and you lose this kind of a loop, this circuit. So the electricity can no longer flow. So the iron armature will simply spring backwards because this electromagnet is now turned off and won't be attracting the iron. But if you look, the moment it springs back, it rejoins the contact. And if you rejoin the contact, electricity will flow again. You'll turn the electromagnet back on, and this hammer will come right back and hit the gong. So for as long as somebody has their finger on the switch, you will continually bring this iron armature to the magnet and hit the gong and back. It will hit the magnet, then because the electricity is broken, or the circuit's broken so no electricity can flow, it springs back. When it springs back, it gets attracted to the magnet again because the circuit is now complete, and springs back and hit the gong. So this iron armature is literally just springing back and forth so long as somebody has their finger on the switch. And that's how electromagnets are used in an electric bell or a buzzer. Okay, hope that helps.